Namana, just making sure. Am I audible?
Yes, Devendra, perfect.
Thank you, thank you. Uh, Human brain is so intricate machine that we cannot judge about its actions or thoughts instantly. Never mind, it is so powerful even to study about tiny objects from atoms to as large as the black hole out there. Its essence can be seen that without even physically touching them, we are at a stage to study astronomical objects, say a black hole, without even going near it. And surely no one wants to go there. But there are a few questions that are still mysterious. Like, what was the source for the universe to begin? And if it had begun, then how would it even end? A quote from Robert H. goes like this, that it is difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. The reason for suddenly bringing this quote in between the context seems apt for the mysterious questions mentioned before. A very good evening to one and all present here. I am Devender, currently pursuing BTech in Aerospace Engineering, would welcome you all with immense pleasure for the second day of our outreach program. Welcome all. Now, I would like to introduce Namana Siriam Gowda, who is also pursuing her BTech in Aerospace Engineering, will be accompanying us as the co-host for the day. At SSERD, we offer online courses, workshops, projects, and internships on wide range of topics related to space, astronomy, and aerospace sectors. For more information, please check out our official website. I thank Genex Space and the Space for sponsoring and collaborating with us. Now, let us dive into the voyage of space all the way through Milky Way, exploring things from Big Bang to from Big Bang to dark matter. Today, on the panel, we have Dr. Prajwal Shastri, who is an astrophysicist and an adjunct professor at International Center for Radio Astronomy and Research, and Devika Kamath, who is a senior lecturer in astronomy and astrophysics at Macquarie University. Now, I would like to introduce the moderator for today's session, Khushi Jirawala. Khushi has done her undergraduate in BSc Physics from St. Xavier's College, where she had published her first research paper on IEEE. Not the end, she has also presented her work in many places, including Space Application Center at ISRO. She loves to play chess and enjoys doing mathematics. Since she is a good science communicator, we have her here as the moderator for today. She is now currently pursuing Masters in Physics from NIT Rourkela. Welcome, Kushi. And now I request Kushi to take over the meet and introduce the speakers for the day. Kushi, over to you.
Yeah, thanks a lot, Devendra. Well, I'm very excited to introduce today's panel. We have here prominent people with us this evening, Dr. Prajwal Shastri and Dr. Devika Kamath. Speaking about Dr. Prajwal Shastri, born in Bangalore, they did their bachelor's from St. Agnes College, master's in physics from IIT Bombay, and PhD from TIFR Mumbai. They went on to become a faculty at Indian Institute of Astrophysics IIA Bangalore for 23 years. They have been an astrophysicist pretty much all their life, their core research interest being the empirical investigation of giant black holes that are found in the center of distant galaxies. Gathering and using the data obtained from telescopes that operate from radio to gamma ray frequencies, they focus on the phenomenology of accreting supermassive black holes. They are deeply concerned about the gender disparity in the sciences and have constantly encouraged people to break this barrier. As indeed, when it comes down to doing science, or anything for that matter, gender and age should be the last thing one should worry about. And as the saying goes, women can do everything a man can, and they can do it in heels. Easily one of the nation's top astrophysicists, Dr. Prajwal believes that scientific thinking should be a way of life, regardless of what people do. The scientific method is the best method if we want to understand nature, they say. Now, speaking about Dr. Devika Kamath, spending hours as a child with her grandfather, pretending to navigate through oceans using the night sky, a sextant, and a telescope, she decided to become an astrophysicist at the age of 13. And not to our surprise, she is now a stellar astrophysicist and a senior lecturer in astronomy and astrophysics at Macquarie University, Australia. She is internationally recognized for her work on observational studies of dying stars and their implications on the origin of the elements in the universe. On winning the International Postgraduate Research Scholarship, she left the small town in South India to pursue a PhD from Australian National University, where she pioneered a hunt for rare stellar fossils, dying stars. This provided a gateway to reconstruct the life of stars and investigate their evolution and alchemy. During her postdoctoral research fellowship in Belgium, her discovery of a new class of stars proved that the evolution of stars in our universe is more diverse and complex than the standard theories predicted. Having produced over 50 scientific publications and won competitive access to telescopes around the world, Dr. Kamath has recently been awarded the prestigious Australian Research Council (DECRA) Fellowship to further develop their research. Announced by Science and Technology Australia (STA), she was one of the three Macquarie's 2018 STEM Superstar. Alongside this, she is actively involved in student training and outreach programs that benefit Australia's STEM community. I am very delighted to welcome both of you to this virtual stage of ours. Now,
Thank you, Kushi, and it's a pleasure to be here.
yeah, I'm sure there's a lot more to your journeys than what I've managed to speak so briefly, but it is inspiring for students like us, and we look forward for today. We'll all learn something new. Well, I'll quickly address the proceedings of the evening. Starting up, we'll have Dr. Prajwal, who shall be speaking, followed by Dr. Kamath, and then we'll have a live Q&A session where our audience will be asking questions. Over to you, Prajwal, ma'am.
Thank you very much. Hello, everyone, and it's a pleasure to be here. I love Space Week, especially because, I was born almost exactly a year after Sputnik was launched. And it was a time when science was very thick in the air. And Yuri Gagarin and Valentina Tereshkova were my childhood heroes. And so this is a very special occasion. So, as I said, when I was a child, science was pretty thick in the air. And when I was about 8 years old, my parents got me a book, and it was called The Atom. And it was this really beautiful book with color illustrations. And it had an illustration of Rutherford's experiment. Unfortunately, I don't have that book anymore, so I don't have that beautiful illustration. So I just picked something from the internet to remind you. But basically, it was an experiment where he put a gold foil and shot particles at it, and some of them bounced back most unexpectedly. I thought that was the coolest thing in the world. And I really wanted to be a scientist at that point. Around 11, my parents gave me Madame Curie's biography to read and a fantastic science fiction book called Andromeda. And then there was this absolutely fantastic book on mathematics by William Sawyer, which really, for me, described and explained what mathematics really is. So I luckily read it very early. So mathematics no longer was a subject in school. It was a language. It was an approach. And of course, later on, I bought this book, which is one of the most successful mathematics books ever, which has sold over 500,000 copies. And I just wanted to mention that in Pune, there is a William Sawyer memorial, which contains a lot of his writings, even his handwritten notes and so on. So that is something you may want to look at. At that time, not only was science thick in the air, it was possible to actually feel this exhilaration about the night sky. So it was quite common for us as a family to put a mat on our garden after dinner and watch the night sky, the stars, the meteors streaking across, and even the Milky Way. Even though I grew up in a town which is not that small a town called Mangaluru, I could see the Milky Way after dinner. And sadly, that's no longer the case. But obviously, the stars have ignited the imagination of humanity for a very long time, since ancient times. And there are many beautiful legends. For instance, the Vaiga people, who are the first people from Madhya Pradesh, central India, have a legend of how a stone from the catapult of a hunter shatters the eggs of a pigeon, and so the eggshells scatter everywhere and become stars. Similarly, down in Australia, there is the legend associated with the Milky Way. The Milky Way is a band across the sky with bright patches to the stars, the dark patches which are the dust particles that hide the light from the stars, and they talk about the emu which soars in the sky. Today, of course, we know that most of the dots that we see with our naked eye are stars like our own sun. You will hear more about this in Dr. Kamat's lecture. She's the stellar expert. Some of them are gaseous nebulae like this, which form stars. There's, of course, the Milky Way, and there are the planets. And one particular nondescript dot is a galaxy, the Andromeda galaxy, just like our Milky Way. So astrophysicists typically use four approaches, one can say, to study the cosmos. So there are theoretical predictions, they build instrumentation, they observe the sky with this instrumentation in order to test the predictions, and there are computer simulations to compare with observations. So some examples of theoretical predictions are this very old one by Giordano Bruno, who said other stars have planets. There's, of course, Einstein's prediction, which said that masses must bend light. And there's Roger Penrose's prediction, which said that a collapse of a dying star to a black hole is inevitable. So these are just some examples. So astrophysicists measure the cosmos using the whole electromagnetic spectrum, right from radio to microwave, visible light, ultraviolet light, right up to gamma rays. They also use neutrinos, which are these very elusive particles which we have all around us, but many of them originate in the cosmos in very, very specific physical phenomena. And then, of course, there are the ripples in the fabric of space-time itself, which we call gravitational waves, which we are now able to measure as well. So these are some telescopes that measure visible light and radio light, and they're located on Earth. But because the atmosphere is only transparent, more or less, to visible and radio light, if we want to look at the cosmos at X-rays, ultraviolet light, infrared, and so on, we have to go into space. And so there are all these space telescopes. These are just a few examples. And then there is the Neutrino Observatory in Antarctica, one of many. And of course, the Gravitational Wave Observatory, or LIGO. And each of them is, of course, needless to say, an enormous engineering feat. One thing to remember about our studies of the cosmos is that the speed of light is 300 kilometers per second. We don't notice that in our everyday lives, but it is something, it is finite. And so it takes light 1.3 seconds to reach us from the moon. 8 minutes to reach us from the sun. Oh, that's a mistake there. I should have said from the sun. And so astrophysicists are always out of date. They can never know what is happening in the cosmos right now. We only know what happened at a time when the light left us, so left the object. So for the moon, it's very small. For the sun, it's a bit more. And for all those galaxies, it's huge. Now, another thing I just want to mention is, sorry, was there a comment? Okay, I want to mention that I want to talk about what are false color pictures, because what does it mean to take images of the sky in frequency, the wavelengths that the human eye cannot see, right? How do you render them? So this is a typical photograph of a cat, and now if I took an infrared image of this cat, how would I depict it? So a typical way is to use colors to represent the intensity. So that's why we call them false color images, because the colors are not real colors. They just represent intensity. And so we know that the cat's nose is cold and its eyes are warm. And so there will be less infrared light from the nose and more from the eyes and so on. And so this, for example, is a similar image, but again, different colors are used to represent the same. So a false color image has meaning only if accompanied by a key like this, which tells us which color is what intensity, and the colors are arbitrary. So this is the same thing rendered with a different set of colors. The colors have meaning only in relationship to a key like this. So this is an example to show both these things. So on the left is a picture of the planet Uranus, which is the way it would look if we could see it with our eyes. And oh, you can't see my slides?
We don't see your slides, actually, and I was just trying to tell that to the organizers, because you were referring to objects, and
so what should I do? Should I...
Yeah, there will be a share option.
You should have told me earlier, right? Somebody should have called me.
Yeah, I was wondering, and there was a point when you referred to an object, and I said, I surely can't see what she's sharing, and I think the organizers thought you were not sharing slides anyway.
Because I can't see the chat when I'm talking, right? I'm paying attention to the...
Because I was very curious.
Let me try this again, okay? Let me try this.
Yeah, I was very curious to see the image you were showing, and I thought, I can't see what she's showing. It's such a fascinating topic.
Now?
No, not yet. Yes, now we can.
Now we can. Should I quickly go over the slides, because otherwise it doesn't make sense, what I was saying.
Yes, please. Yeah.
Okay. It will mean another 5 minutes or something. Is that okay?
Yeah, sure, not a problem.
Okay. So I was talking about, being born in the year after Sputnik and all that. This is an image of Sputnik, and that's Yuri Gagarin and Valentina Tereshkova, who were my childhood heroes. And that is the Rutherford experiment that I was talking about. I'll just zip through these because you can, I guess, look at the YouTube video afterwards. That's the Milky Way, and this is not a picture from my childhood, but I could see it like that. That was the legend of the Baiga people. That was the Australian emu, and yeah, so this, I think I can zip through. So that was the only other, the only dot in the sky that we can see with our naked eyes, which is a galaxy other than the Milky Way. So I was saying that there are 4 approaches to astrophysics research. The first is theoretical predictions and affirmations, and examples of that are that what Giordano Bruno said, that other stars have planets. Einstein, for example, said that masses must spread light, and Roger Penrose concluded that collapse to a black hole is inevitable. And so then I went on to say that astrophysicists measure the cosmos using the whole electromagnetic spectrum, using neutrinos and ripples in the fabric of space-time, that is gravitational waves. And these are examples of such telescopes. So these are visible light and radio light telescopes, which is on Earth. And because the atmosphere is not transparent to the other frequencies other than visible and radio light, we need to have telescopes launched out into space in order to study the cosmos at these frequencies. And here is an example of a neutrino observatory in Antarctica and the LIGO observatory, which measures the ripples in space-time. So you can see this all is okay.
Yeah, everything's fine. Everything
Okay,
is fine.
so I just request you to actually call me or interrupt me on the audio if you have to tell me something, because I can't really pay attention to the chat while I'm giving the talk, okay?
All right.
So I was saying that each of these is an enormous engineering feat. So I was explaining that astronomers are always out of date because light has a fixed speed, and so it actually takes 1.3 seconds for light to reach us from the moon, and 8 minutes for light to reach us from the sun, and then much more time for light to reach us from different things in the cosmos. The other thing I wanted to describe was what false colored images are, because I will be showing images of the cosmos which are taken at different frequencies that the eye cannot see. And so the question is, how do we render them? So this is a picture of a cat, and if you took an infrared picture of a cat, the one way to render it is to use colors to represent the intensity of that image, the intensity of the infrared light. And so the colors are arbitrary. And so we know that the cat's nose is cold and the ears are warm, and so there will be more infrared from the eyes and ears rather than from the nose. And that is what is shown in this infrared picture. The second infrared picture is the sort of similar thing, but with different colors to represent the different intensities. So in other words, a false color picture has meaning only with a key like this, and the colors are arbitrary. So this is the planet Uranus, and I've shown the same image. On the left is the true color image, and on the right is the false color image. So the left is how the eye would see it if we could see such a sharp image of Uranus, and on the right is a false color image of the same thing. So here's a galaxy that you have perhaps all seen, and this is a Hubble Space Telescope picture of it. And it's a true color image. In other words, it's very close to what the eye could see if the eye could see such sharp images. And here is a bunch of false colored images of the same galaxy, false because they are at different frequencies. So in the middle, this is the same visible light image that I showed you earlier. This is an X-ray image, and you can see that there is emission coming from a very different kind of a distribution, because the same things that are bright in visible light are not bright in X-rays, and sometimes vice versa as well. And in the middle, you see this dark band, which is due to the dust particles that occupy that part of the galaxy, and they glow in the infrared. And so when you take an infrared image of the same galaxy, that what is dark here glows here, and this is a superposition of all these different false color images. So that's just to give you a sense of what false color images are. These are real images of different galaxies, and this is a superposition of the image of a galaxy taken in visible light and taken in radio light. So the pinkish stuff is the image taken in radio light, and that's superposed on the visible light image. In the visible light image, you see the galaxy with all the stars in it shining, and these are all background galaxies and so on. By the way, can you see my cursor as I move it around?
Yes, yes, we
Okay,
can.
these are foreground stars and these are other background galaxies, but the radio image shows that there is no radio light from these other galaxies, but there is radio light only from this one, and it is visible in the form of two sort of jets that then diffuse out into these lobes. And this is because we know now there is plasma there, which is squirted out of the center of this galaxy, and it creates synchrotron light, which is what we see and can measure. This is another such example, and here this galaxy is something called Messier 87. So here on the top left, is a visible light picture of the galaxy where what is shining are the stars in the galaxy. And this is a radio picture, and you can see that there are these jets of plasma which are occupying a huge area in the sky, which means a huge volume in the sky. There are many examples of this, and the only way that we can explain all of these is by saying that there is a giant black hole in the middle of these galaxies. So a black hole itself, of course, is dark. It doesn't emit any light. And so then how do we get all this? Well, because the black hole is a center of very strong gravity, any matter that comes close to it swirls around it because it's sucked in. But before it's actually sucked in the process of swirling, it gets heated and shines, and also produces plasma because of it getting heated. And all of this plasma is not able to plunge into the black hole because it also generates magnetic fields. And these magnetic fields land up twisting and driving some of the plasma into these jets, which then leap out not only of the black hole environment, but out of the galaxy itself into intergalactic space. So this is just a visible light picture showing that the actual galaxy is very nondescript, but then when you image it with a radio telescope, it shows these lobes. So I said that the fourth approach to astrophysics is computer simulations. What that means is that you put a bunch of particles in the computer, meaning to say you program a bunch of particles with some positions and speeds. And this is an example of a computer simulation which uses the physics we know from general relativity and the physics we know from magnetized fluids, and put all that together, put a magnetized fluid near a black hole and see what happens. And we see that, and we see that the matter lands up swirling around the black hole and eventually, of course, into the black hole. But in the process, because of it getting heated, it produces plasma, magnetic fields. So the magnetic fields are represented in this simulation by the green lines. And so some of that plasma is the blue stuff, which is launched out into these jets and into intergalactic space. So what this computer simulation is telling us is that the physics we know can indeed explain why we see these jets of plasma and lobes that are surrounding these galaxies. So this is another example of a simulation where two galaxies are coming together. So you can see when they come together because of the gravitational interaction that the stars are all completely disrupted from their orbit. So the two galaxies then merge to form a single galaxy, and the central black holes in each of them will also, that's what the simulation predicts, that the black holes will also come together, spiral around each other, and eventually coalesce to form one big black hole and also produce a bunch of gravitational waves, which can be detected with an observatory. However, I should just mention that they can't be detected with the current gravitational observatory. They need a more sophisticated one, which is planned to be launched into space. This is an example from my own work where there is this galaxy called the Karak galaxy, which is interacting gravitationally with these other two, and itself is, we know now, a merger of two galaxies, similar to what I just showed you happened in the simulation. Of course, we can't watch it happening because it's happening on a very large time scale, but what we can see is a snapshot, and we can see by looking at it at different frequencies, we can see the effect of this merger. So this is an image taken with the Australian telescope at Siding Spring, and the same thing imaged at radio frequencies with the Australian radio telescope. This is an infrared picture which was taken much earlier, and all of them show evidence for these two supermassive black holes that have the swirling matter around them, shining in visible light, shining in radio light, shining in infrared light, and also shining in X-ray light. So we have a Chandra telescope image as well, and the two objects are shining in X-ray light as well. So just to very quickly give you a sense for black holes, black holes can be understood with high school physics in a way, because you remember the idea of escape velocity. So if you stood on the surface of the earth and threw something, it will fall back to the earth. You throw it faster, it will go a bit further, but still fall back to the earth. But there will come a speed with which, if you launch it, it will not, in fact, come back to the earth. It will, in fact, escape from the earth. We call that the escape velocity. And for the earth, at the earth's surface, for the earth's mass, it's about 11 kilometers a second or 40,000 kilometers an hour. For the moon, it's much lower, 2 kilometers a second. And we know that we can quantify this by this relationship between this thing we call the escape velocity and the mass of the object and the distance from where we are launching the object with respect to the center of the object we are trying to escape from. And so suppose you take the mass of the Earth, for example, and you keep the same mass but squeeze it to a smaller size, then what happens? Then what happens is that the escape velocity at the surface increases. So suppose you now imagine the speed of light, which is 300,000 kilometers a second, and you imagine that you squeeze the Earth so hard that its escape velocity becomes equal to the velocity of light. This is just a hypothetical experiment, of course, but what happens is, it turns out that if you do this and write down the formula, you get a relationship between the size and the mass of the object. So if the escape velocity has to be the velocity of light, which means even light cannot escape from this object, then the object has to be squeezed so hard to obey this relationship. And it turns out that for the Earth, you have to squeeze all the mass of the Earth to a marble size, and then it will not let even light escape from it. In other words, it will become a black hole. So now the question is, if the only way to explain these giant jets of plasma that come out of the center of the galaxy and get into intergalactic space is to say that there is a giant black hole in the center of these galaxies. So that means that at the very heart, this is the distribution of stars, so at its very heart there should be a giant black hole. That suggests that all galaxies should have a giant black hole in their center. So the team of an astrophysicist called Angier in California decided to look for this object, and they used a telescope called the Keck telescope to do this. Now, what are the challenges? There's one challenge already, which I hinted at earlier, which is these dark patches in the Milky Way, which are due to dust particles and they obscure the light behind them. And so it's not possible to reach the center of the Milky Way in visible light. So that's one challenge. The other challenge is if you're looking for something like a giant black hole, even if I'm using the term giant black hole, it's actually, relatively speaking, very, very small in the larger scheme of things. You need very, very sharp images in order to get at it. And the atmosphere doesn't help us because there are density changes in the atmosphere which result in refractive index changes in the atmosphere. And so a ray of light from a star instead of reaching our detector directly will be made to dance around by this atmosphere, which is what is shown in this animation over here. So that is a real challenge. Now, what Andrea Ghez could do is, first of all, at the Keck telescope, there were infrared detectors. So she could use the infrared light to peer into the center of the galaxy. And secondly, the telescope had an extremely large mirror, a 10-meter diameter mirror, which meant it could collect a lot of photons. And so by doing very fast imaging, she could beat this dancing around of the ray of light and get extremely sharp images. So that was one step already. But the other step was that this mirror, the 10-meter mirror, was not a single mirror, but instead made of hexagonal segments of many mirrors, as you can see here. This is one hexagonal piece. And why was this? This was so that each piece would have behind it controls that could distort each piece. So what they could do is shoot out a laser beam from the telescope into the sky and image that and thereby measure the distortions of the atmosphere and then compensate for those distortions by distorting each mirror segment. So this is done at a very, very fast rate, of course, at a rate which is faster than the atmosphere changes the refractive index, and because of which extremely sharp images could be obtained. So here is a comparison of an image of the planet Uranus without this technique, and here is with the technique. And you can see how the increase in sharpness happens. I'll skip this slide, I think. So this is the image of the Milky Way. You can see the band across the sky and the dark
Excuse
patches.
me, ma'am. Sorry,
Yeah.
but there's some noise coming as well.
Some noise?
I'm not sure if. Okay, now we're
Is it?
fine.
Okay.
Yeah.
Okay. Shall I continue?
Yes, sure.
Okay. So this is the Milky Way, and this is a picture taken from Ladakh. You can see all the stars, the billions of stars in the Milky Way, the dark patches due to the dust particles, and you may be familiar with the Sagittarius constellation. The center of the Milky Way is very close to the tip of the spout of that constellation. So this is where Andrea Ghez's team pointed their instrumentation. Now, I will show you the data that they got. But in order to do that, I first want to, because it's in the form of an animation, I first want to explain what it is. So what they did was to take pictures of the very center of the Milky Way. And what they found there was stars emitting in the infrared. So what this shows you is a typical picture that they took. Each of these multi-colored dots is a false color image of a star. So this whole thing is a false color image. They're labeled, of course, artificially. And this white star is not real data. It is just marking a position in this piece of sky. And you will see right away why that particular position is being marked. And on top, right here, is a counter which tells you the date at which the image is taken. So they took a bunch of images starting in 1995 and continuing right up to now. And they put all these images one after another to make an animation so that you can see the shifts in the position of the stars and therefore how these stars are moving. So remember, these are stars in the very, very center of the Milky Way, and they're able to see it because of the very, very sharp images that they're taking using the techniques I just described. So here is the animation, and you can see that the counter on the top right is running and showing you the date, and you can see that the stars are moving. So what strikes one immediately from this is that firstly the stars are not moving in random directions, right? They're going along very definite paths. They're all going along what looks like elliptical orbits. One particular one even completed its orbit, this one. And all the elliptical orbits have the same focus, which is marked by that white star. So what does this remind us of? This is exactly like the planetary motions in our solar system. And we know why that is. We know that the mass of the sun drives all these planets in elliptical orbits with the sun as one of the foci. So these stars, here they are not planets, but here they are stars, which are in elliptical orbits around the sun as one of the foci. Elliptical orbits around this point as one of the foci, but there is nothing at that point itself. There's no infrared emission coming from that point. So the only explanation is that there is a mass there, which is driving all these stars gravitationally, but it is not emitting any light. One more thing to remember is that this star in particular, which approaches very close to that point which is marked by the white star, it emerges afterwards in its elliptical orbit. So it's not disrupted, it's not sort of going off deflected into some other path. So this means that whatever that dark body is that is driving all these things in elliptical orbit has to be smaller than the closest approach of this star with the smallest elliptical orbit. So putting all of these things together, firstly, just with the orbits, knowing the speed and knowing the period, you can determine the mass of the thing that is driving all these things. And you can also get a limit on the size because of what I just said, because the closest approach star is actually emerging from its elliptical orbit, right? So, sorry. So therefore, Andrea Ghez' team was able to conclude that there must be a giant black hole in the center of our Milky Way, and its mass is about 4 million times the mass of our sun. So now let me go back to this picture of a galaxy called Picture A, which also is a superposition of visible light and the radio image, and it shows these jets of plasma that are squirted out of the galaxy into intergalactic space. Right? Now, think about what I said about the black hole. A black hole is one where you squeeze it so much that even light cannot escape. Therefore, it is a very strong, it has a very strong gravitational field around it. And just like the sun or even the earth does bend light, you would expect that if there was a black hole against the background light of the stars, the light from the stars around it would be bent and you would see this distortion. This would be really the really sure shot way of saying that there is a black hole at that position. However, it's a very difficult thing to do because the light from the background stars is not that bright. And so the kind of contrast that we get is not that high. Apart from the fact that, I mean, even though this may be a very big black hole, it's still in the larger scheme of things extremely small, and so we don't have such images. However, if you have something like this, where you have matter swirling around the black hole, and therefore getting heated and shining, then something like that would provide a much better contrast between the black hole, the dark part of the black hole, and the things surrounding it. So in other words, if you had an ordinary dark object and you had matter swirling around it, which was shining, you would see a silhouette something like this. On the other hand, if it were a black hole, it would be like what we saw in Gargantua in the movie Interstellar, namely that the matter would be swirling around, it would be shining, and therefore we would see it, but we would also see the light from the matter which is behind the black hole because it would come curved and reach our telescope. So that's why you would see this sort of hat shape to the uh, light around the black hole, which is very similar to this, except that here the contrast would be much higher because it's not just background light from the stars, it's actually the shine from this plasma, which is pretty hot and pretty bright and shining really very bright. So this is just to show you that this galaxy called Messi 87 is a nondescript dot in the larger scheme of things, but when you zoom in, you can see the galaxy or the stars in it. This is a zoomed in version where you see all the stars, and in radio light, it looks like this. And a zoomed in version shows you the actual jet on a smaller scale. So this is a radio picture, a false color image of this bit right here. The same thing in visible light with Hubble Space Telescope, and the same thing in X-ray light with the Chandra Telescope. They all show this jet, which is in this part of the picture. And on a larger scale, there is huge amount of plasma, which has gone to very, very large distances. Now, this galaxy was observed with an instrument which was called the Event Horizon Telescope. So this is actually not a single instrument. It's a bunch of different telescopes which are placed on different continents, in fact. But they all look at the same object, in this case, Messi 87 and its core. And the light, the radio light from all these telescopes is combined, but combined in the voltages and the signals so that you have information of the both the amplitude and the phase of the signal that you're getting from the sky. And then if you Fourier transform this, you actually get a very, very sharp image of the sky. In fact, the sharpest image that we've been able to get ever. So this is Katie Bowman, who led the team that designed the algorithms to do this whole Fourier transform and image analysis. And they looked at the very center of Messi 87, and this is what they found. In other words, a silhouette of the black hole. So I'm coming to the end. Can I take a couple minutes more?
Sure, ma'am.
Okay, so now I want to sort of zoom back and think about what does the sky contain. So if it turns out that if you look at a piece of sky that is just a tenth of the size of the moon, and the Hubble Space Telescope did this many years ago, you find that there are 10,000 galaxies in just that tiny patch. So virtually every dot and smudge here, except for these cross-shaped things, is a galaxy. And there are 10,000 galaxies in just this tiny patch, which means you can imagine now that the universe is simply filled with galaxies. So each of these galaxies has billions of stars. Each of them has a giant black hole in the center, swirling planet. Each of the stars has the possibility of our planetary system. However, we have not so far seen a planet like the Earth. And this is an important message that with all the space exploration, we have not even reached the edge of our solar system. We have only explored a few planets around, but none of them are a planet B to Earth. So the Earth is special. It is a pale blue dot that is floating in the cosmos. You remember this picture that was taken by the astronauts in Apollo 8, which is one of the first pictures of Earth, real picture taken from outside. And one of the journalists said these words about how, I won't read the whole thing because I'm out of time, but you should read this quote because it's a very touching and moving quote, which says, what we see is just this one fragile planet making its way across the vastness of space. So there is no planet B. So we do need to take heed of what Gandhiji said. The earth is sufficient for everyone's needs, but not for everyone's greed. And I want to leave you with this quote by Mae Jemison, one of the very famous astronauts. And with that, I will stop. Thank you very much.
Thank you, Dr. Prajwal. Over to you, Devika ma'am.
Thank you, Prajwal. That was just so fascinating. You took us on a journey to the universe, and I'm sort of still lost in space somehow. So that was so very interesting. I could have listened to you forever. I think I would like to start by, thanking the organizers, including Nikita, for giving me the opportunity to come and present and share space with the amazing Prajwal ma'am. So this is amazing. And I know a lot of work goes into organizing an event like this. So also thanks to all the organizers here. Let's see how the next 30 minutes goes. And I hope to share with you a little bit about my passion for astronomy. So I'm going to try and share my screen. So feel free to pop in at any time and tell me if something is not right. Okay. All right. So I hope you're able to see my screen. Yes, okay. All right, so today I would like to take you on a journey of a topic that is very close to my heart. And Kushi gave a very kind introduction about my journey and what I do. So indeed, I wanted to explore the universe and befriend the stars since I was a child. And what I'm going to talk to you about today is what I like to call cosmic alchemy. It's basically understanding the origin of chemical elements in the universe. It seems like a rather straightforward question with a straightforward answer, but the answer is actually quite complex and in fact long-standing for centuries because we still haven't put our finger on the answer as of yet. But I thought that because it is, we are celebrating women in space and, if I may add, science in general, I would like to share that at a very impressionable age, I'm talking about between 10 and 11, I was fascinated by one amazing woman in science, in STEM, Madame Marie Curie. Now, the story for me begins with being presented with a bunch of these stick on the ear glow earrings. I think some of you would have had them as children. And at that time, I was told that the earrings were made out of radium, and I'm so glad that that was not true. I don't think I ever wore those earrings, but I did spend a lot of time in my school library trying to figure out more about radium. It was such a fascinating element because I thought that that's what was making it glow. And I realized that radium was discovered by Marie Curie and her husband. And in fact, in 1911, she got a Nobel Prize for chemistry for discovering polonium and radium by coming up with a technique to isolate radioactive isotopes. So for me, in my head, when my mom was baking cakes, I thought, wow, cakes are yummy, but chemical elements, I wish I could cook them. I wish I could discover elements. And then to top that, I realized that Marie Curie also championed the discovery of X-rays. I mean, as kids, we all love looking at X-rays because it's so spooky. And with Halloween in the corner, I think it's just perfect. So for me, Marie Curie was my star. I wanted to be like her. And when I was a child, I grew up pretending to be her, pretending to make elements. And I kind of role played her a lot. Now, that combined with the fascination for stars that came from my grandfather, because he was a sailor and we used to look at the night sky a lot and pretend that we were navigating using a sextant and a telescope. All of that together led me to being very protective of that dream of being an astronomer, and also somehow working with the chemical elements. And the pursuit of that dream kind of took me all the way from a little town in south of India to Australia, where I did my PhD. And because I was working on, studying the evolution of stars and the production of elements, a lot of my work involved observational astronomy. This essentially meant that my destinations were predominantly going to be where they were fantastic observatories. So after my PhD, I wanted to explore the world a bit more, and I moved to Europe and Spain. And then I also spent a fair bit of time in South America, because that's where we have one of the leading observatories. In fact, quite a few observatories that we use a lot of data from. And finally, in 2017, I came back to Macquarie to pursue an academic role. So this is kind of a little bit of my roadmap, and it's been a fun ride. Not always straightforward, but definitely lots of fun. Essentially, my research during this whole time has kind of evolved, so to speak, into focusing on dying stars or evolved stars. I like to call them stellar fossils, and I will tell you why in just a few minutes. And the core theme of my research is kind of categorized into 3 bins. As I said, cosmic alchemy, which is what I'm going to talk to you about today. And I also work on understanding binary systems. This is when, you and I have friends and we get into relationships. Stars can do that too, and I'll touch upon that today. And when that happens, the system immediately becomes complex. So that's something I also work on. And finally, Prajwal mentioned today that, the Earth is very unique. It's the only habitable zone hosting life as we know it, and that is very correct. But what we find is dying stars, so stars that are like our sun, they get older, and then they expand, and then they contract. Sometimes when they're in a binary system, we've discovered that it can have an accretion disk, very similar to an accretion disk around a black hole, but just not relativistically that high. So kind of low energy accretion disks. And in these disks, you can have planets for the second time. So we call them second generation protoplanetary disks. And of course, astrophysics is the most collaborative science you'll find. And here's a few of my collaborations. You might identify this particular one, the Indian Institute of Astrophysics. And I finally also want to take a moment to highlight my group of PhD students, because I think that they, and so are a lot of you listening, are really the future of what our science is going to be. So lots of credit to all the work that goes in by the entire team. Okay, so that's enough about my journey. How about I talk a little bit about the universe's journey? Because the star of the show is obviously the universe, right? So what I have today is I have a simulation, and this is how it goes, and I'm going to talk you through the simulation. Now, this simulation is done by the illustrious collaboration based at NASA and Harvard CFA. Now, what this illustration shows you is what we understand as the origin of our universe, an event that we call the Big Bang, essentially. So this simulation, as you see, involves cosmological simulations of the evolution of the universe, spanning the initial conditions all the way from time t = 0, which is the origin of the Big Bang, to present day, which is about 13.7 billion years old. Now you can see the colors here indicating dark matter and then slowly gas temperature, because when the universe started, we believed that it was just a lot of photons and high energy radiation. Then through a lot of phases, which I won't go into because of time, we eventually, at about 4.4 billion years after the Big Bang, we started forming the first set of elements and stars and gases. Now you remember when the very first stars were formed, they were simply made out of hydrogen because the universe was made out of hydrogen. Hydrogen, in fact, is the simplest, it's just one proton, right? So it's a very easy element to make. But then eventually, as more stars were formed by the congregation of gas and dust, they started making heavy elements, and that's starting to happen about 8.7 billion years after the Big Bang. If you look at the sun was formed around 9 billion years after the Big Bang. So the sun's age is about 4.4 billion years at this present day. So this is when you see all these red gases representing heavy elements in the universe. So as generations go on, stars have started becoming more and more metal rich. Of course, there's complications, but for the macroscopic level of things, stars get metal rich. And eventually you'll end up with what we have today, which is a webbed structure of galaxies, inside of which there's a lot of stars, and then there's dark matter, and of course, the very mysterious dark energy. Now, this simulation that you're seeing here took around 19 million CPU hours. And I'm not talking about laptop hours, I'm talking about supercomputer hours. In fact, one of the supercomputers was called the Curie supercomputer after Madame Marie Curie. So she's quite a significant person in all branches of science. And it used almost around 8,000 CPU cores. So if you're someone who's into astrophysics and computing, then this is definitely a field for you. So come on in and join us, okay? But having said that, coming back to the question that I care for about a lot is something along the lines of, so what is the universe really made of, right? And I don't have an answer to that question. Let me put it out straight away. So the universe, most of what we see or what we think we know of is basically unknown. It's dark energy. We call it dark energy for a lack of a better term. It's sort of almost like a fudge factor that you need to reproduce the model of the universe that cosmologists find. There's 23% of it, which is dark matter. Now, dark matter you can actually detect because it has matter, it interacts. And in fact, X-ray observations that have come out over the last decade has pointed evidence of the existence and also location of dark matter. The other 5% or so is essentially baryonic matter, right? So all of this is non-baryonic matter, and this essentially is the baryonic matter, which is you, me, the dinner you're gonna have tonight, the stars, the galaxies, and all of that. So all of that is essentially like around about 5% an order of magnitude, which is the error bars you normally represent in astronomy. If I split that 5% into understanding the core basis of it, I find that most of it is hydrogen, because that was the element that dominated the universe when the universe was created, one single proton, the hydrogen atom. And then you have a little bit of helium because hydrogen happens to fuse into helium, and that happened also during the creation of the universe. And we call these primordial elements, hydrogen, helium, a little bit of lithium and beryllium. After that, what happens is the universe started cooling down, and none of the elements could be made until the first stars were formed. And this slither that you see over here is the heavy elements. So if you're gonna like look at your blood and it's got iron, all of the iron in every single one of us and every other thing that is made of in this universe, in addition to hydrogen and helium, is comprised with this tiny little 1% of what we know of the universe. Isn't that fascinating? But what is even more fascinating is that we're still trying to figure out how exactly this 1% of the heavy elements and also sometimes helium comes about. And I hope that, you know, in the end of the next 10 minutes or so, I'm going to take you through that journey. Now, I've talked about my evolution, I've talked about the evolution of the universe, so it's only fair if I talk about you as well, right? And I am a researcher and I do social media. So what I've done is I've gone and researched about every single one of you, and I'm sorry if this is going to embarrass you. I found a very, very old picture of all of you that I'm now going to show. And pretty much here it is. This is a very, 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 very old picture of each and every one of you, because we share a profound connection with the universe. The elements made in stars are the very same elements that make up our bodies and everything around us. So if you take the human body, we actually carry inside us a significant piece of the universe. The oxygen, the carbon, the hydrogen, the nitrogen. That's not all. If you look around you, the toothpaste you use in the morning, it has fluorine. The laptops and cell phones that make our lives kind of good and bad, that has silicon. The lithium in batteries, salt, gold, if you like it, whatever you may take, right? So the question is really, the universe and cosmic objects make these elements, but how? How do they do this? And that's kind of what this particular branch of astrophysics tries to answer and tries to tackle. So we've all come across a periodic table, right, in the past. And here's the astronomer's version of a periodic table. I take this from the NASA website simply because I'm in the process of creating my own, but being a perfectionist, everything takes me longer than it should. So here's the NASA one for now. So what you find here is hydrogen and helium, and you see that they're color-coded, being primordial elements to Big Bang origins. You then have dying low-mass stars, you have merging neutron stars, you have exploding massive stars, you have white dwarfs, and cosmic ray fission. If you're sitting there and thinking, wait a minute, Devika, we have the sun and all stars are the same, well, here I'm coming to tell you that actually not all stars are the same. And you might know this, but for some of you who don't, here's something that I'm going to tell you that's going to blow your mind away. First of all, not all stars are the same. Second of all, stars can be of different ages. In fact, once again, we're very connected to stars, and I'll tell you how in a minute. But have a good look at this periodic table, because we're going to come back to this and kind of see if we can piece this together. So a lot of the elements are made from exploding massive stars and also merging neutron stars, and of course, dying low mass stars. Now, this is kind of where I come in. Now, if you look at the element iron, which is if you've done a little bit of nuclear physics in your undergrad, you'll know that the binding energy of the iron nucleus is so large that it's very hard to rip apart or fuse the iron nuclei. So how do you make all these other elements outside of iron? I mean, you can burn hydrogen to get helium, helium to get carbon, nitrogen, and you can do that, by burning processes. But once you come to iron, how do you burn iron? Even in a star, it's really, really difficult. So how do you make all these other elements? Let's see if we can answer that question. But before that, like I said, now you and I, we are born, we get older, teenage, difficult years, we become adults, hopefully mature adults, some of us at least, and then we get older and we die, right? That's you and me. Stars do exactly the same thing. So if I can go forward, stars do exactly the same thing. Stars are born in what I like to call stellar nurseries. Let's take the sun. The sun's like a teenager now. And if you have a teenager at home, you know that, or if you remember your teenage times, we don't do much. We're kind of like dragging our feet. And the sun's doing something very similar. It gives us life, and I love it. But in terms of chemistry, it's simply burning hydrogen into helium. So it hasn't yet started kind of doing its thing, right? But eventually, when the sun gets older, it's going to become a red giant. And that's when it's going to become chemically really active. It's going to take the helium, fuse it into carbon, take the carbon, fuse it into oxygen and nitrogen, and then it's going to do these magical things that I'm going to talk about and make elements heavier than iron. Eventually, a star like our sun is not going to explode into a supernova. It's going to remove its jacket like you do when you go home, and it's going to become a beautiful planetary nebula and eventually die as a white dwarf. But just like you and me, some babies are born light and some babies are born heavy. Stars are the same. Some stars are born like the sun, but some stars are born much more massive than the sun. Now, when a star that is much more massive than a sun is born, it goes through its life very quickly, and it doesn't do this beautiful peony thing. It does something equally beautiful, but also very violent, and it explodes as a supernovae. So it's important to understand that all of these different evolutionary phases contribute very differently to the origin of chemical elements in the universe. And I hope that in the next, say, 5 minutes or so, I'm able to tell you a little bit more about that. So, for example, like I said, if I start this all over again and I show you the video here, what's happening here is you're looking at hydrogen fusing into helium. Helium is denser than hydrogen, so it kind of starts settling in the core, right? And this is what happens time after time after time. So you get like this onion ring layer with the heavier element that is synthesized sinking into the bottom. Now, for a star like our sun, it will stop with carbon and oxygen because it doesn't have any more mass to be able to fuel the burning of carbon and oxygen. But for a star 10 times like Eta Carina, for example, that's going to go all the way into iron, and then it's going to stop. Then, of course, you get what we call as a supernova explosion, only for massive stars, and then something unique happens in there, which I hope to share with you very soon. So what I show you here is when you rip apart a star and you look inside, you can kind of see the simulation there with the different layers corresponding to all these elements. Pretty funky if you ask me, but moving on, that's iron. So what about all these other elements? Where do they come from? Now here's where I'm going to introduce a slightly new terminology, which is neutron captures. Now we know protons and neutrons are what a nucleus is made of. I think that's kind of basic. So what I show you here is the chemical abundances in our solar system. The sun is a local yardstick. We use that as a measure of understanding everywhere else in the universe because it's like a reference frame, okay, if that makes sense. So what I have here is abundance relative to silicon. You can ignore it if you don't quite understand the terminology, but for now, higher is more abundant and lower is less abundant. And these are mass numbers of the nuclei. So each one of these represent the different elements in the periodic table. So you can see that up to iron, it's quite abundant, and after that, it decreases. But the question is, how do you synthesize these elements? So we'll take a moment to understand that because I think it's quite fun. So what we need is we need a seed, okay? Now, this seed is either going to be a carbon for a star like our sun when it gets much older and it's not a teenager anymore, or if it's a supernova, like a massive star that is going to die into supernova, you've gone a lot and you've synthesized a lot of iron. So we're looking at a carbon or an iron seed depending upon the mass of the star. Now, with some complex astrophysics, which is what me and my team research on, there's a source of neutrons hanging around the star. When these neutrons bombard the carbon or the iron, what you get is you get some sort of an unstable isotope of the same element. So you have elements and you have isotopes because the configuration of the neutrons and the protons in the nuclei simply change. So obviously, if you add more neutrons, you're going to change the configuration of the nuclei. So once you reach an unstable isotope, because it's unstable, it's going to decay. Typically, in this particular case, we're looking at beta decays. Now, beta decay is just a fancy word for saying a neutron converts into a proton. That's all you need to remember. So when a neutron converts into a proton, obviously, it changes the entire configuration of the nuclei, and you're not looking at an isotope anymore, you're actually looking at a new stable element. So neutron capture processes actually happen like this. Let me give you an example. You take iron. Iron has 26 protons and it has 30 neutrons. You add a neutron to it, you get 26 protons and 31 neutrons. That's still stable. You add one more neutron to it, you get 26 protons and 32 neutrons. Now you keep adding neutrons until you reach 26 protons and 33 neutrons. Now that nuclei is unstable. So what happens is neutron gets converted into a proton, and then you get cobalt. For cobalt, you land up having 27 protons and 32 neutrons. So if you follow kind of what I'm saying, essentially you go from one element to another, starting from carbon or iron, not via burning processes, but through what we call as neutron capture processes. Now, these processes have actually had observational evidence, for example, for understanding that neutron capture processes happened in red giant stars, they had to discover technetium. Now, technetium has a very, very short half-life period, which means it decays very quickly. If you observe technetium in a star, it has to mean that the star created it then and there at that time. You know, it couldn't have been created from an old star millions of years ago. So that was kind of how we detected for the first time. And this was done by Merrill in the 1950s. Fantastic game-changing science, right? So coming back to neutron captures, you can obviously see that there's two flavors. And what are these two flavors? Now, these two flavors go back to what I'd like to call the speed at which these neutron capture processes happen. So if you think of that periodic table diagram, you remember they were massive exploding stars, and then they were two neutron stars merging like shown in this particular video here. So ideally, when you have a environment with lots of neutrons, the neutron capture happens much more faster than the beta decay, and therefore you call it a rapid neutron capture process. Now, the time frame for neutron capture processes that happen in rapid form is 1 to 2 seconds. So supernovae obviously make a lot of elements like gold and platinum and so on. But not so far behind are objects that I work on, which is red giant stars. And I'm talking about stars with a mass of about 1 in 10 solar masses. So here's intense convection. So convection is the process by which all stars transfer energy, at least stars that are convective, not the radiative ones. And in this case, also, like I said, you can start from carbon, you can put neutrons in. I won't go into how those neutrons come in, but maybe for another day. And therefore, you'll end up making more and more elements. So what we find is that this is basically a very glorious picture I'm giving you. I'm making it all sound very simple and entire. But it's actually quite complicated because there's a lot of physics we don't understand. For example, what you're looking at, convection. Modeling convection is very, very difficult. Convection is a three-dimensional non-LTE process. And we don't have, at the moment, the computational ability to do that. And the other thing is mass loss. Stars are constantly losing mass. Now, here's a red giant star that has kind of almost died, and it's losing a lot of mass. Now, when stars lose mass, things change around it. So we're still yet to understand and constrain the process of mass loss and mixing inside a star that make all these elements. Now, some of the work that me and my collaborators have done, we found out that stars of a similar mass and similar age, you expect them to make similar elements, right? It's like opening an orange and finding an orange. But what we find is we open an orange and we find an apple. So we've actually found what we call as a chemical diversity in space, and that is something we're trying to sort of understand. Now, this scenario becomes even more complex because in some cases you have the presence of a binary star. Now, one of the things we've discovered, and this was work I did during my postdoc and we continue to do in terms of identifying these class of stars, is a particular class of binary stars where you have the entire life of the star being fatally disrupted because of the binarity. Now, just to give you an idea of what the binary system is, for those of you who are not familiar, the binary system works in terms of gravitational physics, right? So this is what we call as a binary system. Of course, you can have even more complex systems, But as long as two stars are, outside of the limit of their gravity, but still gravitationally bound, you have a nice binary system, all right? So if some of you have watched the movie Dirty Dancing, he says in there...
This is my dance space. This is your dance space. I don't go into yours, you don't go into mine. You gotta hold the frame.
So like Patrick Swayze says, as long as the two stars maintain their Lagrangian Roche lobes, it's all good. But in some cases, and here's a simulation by Thomas Reichert and Ursula DeMarco and their team, you find that the binary pair can kind of merge into each other and form a common envelope and distort things quite badly. So what we found is in some stars, and once again, you might ask me the question, yeah, but Devika, why only some stars? And you'll have to come and work with me to find out the answer to that question, because we don't know the answer to that question. It's just because the universe is really complicated. So in some stars, we find that we have a binary system in the center and we have a circumbinary disk. Now, if you remember the slide I talked about at the very start, that's the disk I was talking about. And this disk, as you can imagine, changes the chemistry a lot. So if you look at a galaxy, guys, we as modelers can predict the number of stars in a galaxy. How does this contribute to the chemical composition of the galaxy? Now, this is based on standard theories, right? But what we find from our work is, first of all, the red giant stars that are supposed to make the chemical elements, all of them don't make the elements. Some of them do, some of them don't. So the amount of carbon they contribute to a chemical galaxy model is actually much more lower than what theory predicts. The second thing is these models don't account for binary stars. And binary stars make 80% of the stars in our universe. So what about the disruption or the pollution of chemistry from binary stars? And that's something we're still trying to understand. Models for binary physics are still upcoming, so it's quite an emerging kind of field. And right now, with all the large sky surveys, because right now we have data for 5 million stars from Gaia and millions of stars from Galah, for example, which are surveys of the old sky, people are beginning to realize that binaries are important. We should be spending more time understanding them and so on. But because I want to keep the time, I'm going to keep going, but we can talk about this more. But before I go on, I want to make another connection with binary stars and humans, because you might have noticed that I've been connecting stars and humans because I think we're so connected. So what I did was, when I was looking at a binary star system, I thought a binary star is a cosmic tangle. That's essentially what it is. And here's my proof. So hold on, let me try and do this again.
Argentina. Buenos Aires.
How cool is that? So you tell me who danced better, the stars or Jennifer Lopez and Richard Gere. So you can choose. But this is amazing, isn't it? And this is why I like astronomy and astrophysics as much. We're so connected. The universe is a part of us. And as much as we do this fantastic science, we can also see that we're not very different from stars, or our lives are not very different from stars. I find that personally very fascinating. Okay, so for the last 5 minutes, I know I've reached my 30-minute mark, but I'd like to quickly answer a very important question, if that's okay. Kushi, can I take another 5 minutes?
Please do.
Okay, fantastic. Thank you. So what I want to answer is, now, I've shown you a lot of this stuff, right? So I've shown you the different types of stars. I've talked to you about the physics. And of course, the questions are how much, how often, all these million-dollar questions. But an even more important question is, how do we know this? How do I, Devika, as an astronomer, or my colleagues study these things? How do we know? So you might have remembered this technique from watching TV and stuff, that there's something called reconstructing the past. You start with the fossil and you try and understand what went on, and you arrive at the start or the life form. I do the same thing with stars. I start working with what I like to call stellar fossils, and I reconstruct the life of a star, how much of chemical elements it has made, and then I try to model that back with my collaborators, and we try and understand what was the initial birth mass of the star, what was the chemistry, did it have a binary companion, and so on. So basically, a lot of my initial work was trying to hunt for these rare stellar fossils. They're quite rare because fossils are rare, even in space they're rare. So we had to find them in 3 different galaxies, our own galaxy and the Magellanic Clouds, and we're now sitting on a really good sample that we're trying to now exploit and answer a lot of the questions. But an even more basic question is, how do we study the universe? Like how? How do we do this? And my answer to that is we simply follow the light. We need light. We need photons. I live for photons. If I don't get photons, I'm not happy. I'm not happy as a person. I'm not happy as a scientist, okay? So photons are my everything. But in order to understand what I do every day and to think about it at home and ask yourself whether you would like to do that, let me tell you what I do. So light has color, right? Agree? We all have color. Today I'm wearing black. And to understand the phenomenon of color, you have to think of light as a wave, not as a particle, but as a wave, okay? So basically, I want you to think of the ocean and light waves just like in the ocean. And sometimes the waves can go really quickly and sometimes they can go really slow. It's just that the frequency of light is so fast or so high that even if it goes slow or fast, our eyes is not sensitive to pick up that waving motion. But essentially, color tells you how fast the light is waving, okay? So every color you see has a frequency. The frequency of light is essentially, like I said, so high that you can't see it as waves, but essentially, for example, violet has a very high frequency. It's a very fast wave, and red has very low frequency. It's a very, very low wave. And wavelength is 1 over frequency. So that's why you have the inverse. So that's light, that's color. So what does Devika do all day? Basically, I work with rainbows all day. I take light, I put it into a prism of some sort, I call it a spectrograph, and I make rainbows, and I work with rainbows. So if you like working with rainbows, you're most likely gonna like what I do. But let me explain that. So I think most of you know the physics of a prism. There's white light disperses into colors of the rainbow. But how does this work in astronomy? This works in astronomy so, for example, you have a planetary nebula or you have a red supergiant. If you put the planetary nebula or supergiant through your telescope, it collects the light, puts it into a prism, a spectrograph, and it's going to give you something that looks like this, the colors of a rainbow, because that's what white light does when it passes through a prism. But the only difference, guys, is you find these dark lines, bright lines, sorry, and these dark lines. And what these lines are they actually represent chemical elements. Chemical elements have a unique fingerprint. Just like your fingers have a fingerprint, chemical elements have a very unique fingerprint too. So
if we shine a beam of white light through a glass prism, the light breaks up into the colors of the rainbow.
So what happens there is that you're shining, oh, sorry, let me go back into that and get my little video going.
If we shine a beam of white light through a glass prism, the light breaks up into the colors of the rainbow, which is called the visible spectrum. If a gas gets in the way of the light beam, it absorbs the light photons of very specific wavelengths, leaving its signature in the spectrum in the form of absorption lines. These absorption lines will vary, depending on the chemical nature of the intervening gas, enabling us to identify the chemical composition of far-off galaxies just by the light that comes from them.
So I thought what she said was fantastic. There was no better way to say it. So I decided to use that particular video to kind of explain what happens when you get these dark and bright lights. So essentially what you're looking at there are these chemical elements, right? And then when you look at it from a spectrograph, what you see is essentially a spectra. So I spend a lot of my time along with other people who are trying to understand chemistry and also like binarity. We work a lot with spectra. So of course, and I think some of these telescopes was also shown by Prajwal, we use a lot of telescopes. We use telescopes on the ground and in space. Now, most of my data is also multi-wavelength. So we study these objects in the optical, we study it in the infrared, in the radio. And the reason is because different parts of the star come up in different wavelengths. So once you put all this together, we try and study the star, the circumstellar environment, and also sometimes the galactic composition, or the host galaxy, as we call it. So I think let's stop here for the care of time. And yeah, let's maybe take questions and have a discussion.
Thank you very much, both of you. I mean, it was just amazing. I feel like it was just a whole journey, you know, from birth to the ending in the black holes. And it was fascinating how Dr. Prajwal mentioned that the technology they use in Keck telescope to get so clear pictures that led to the detection of the black holes, and Dr. Devika mentioning all the different kind of stars and their chemistry and how closely we all are connected in so profound manner. Space is just an amazing topic. It always reminds me of the quote by Stephen Hawking that real science can be way more fascinating than the science fiction. And okay, without any further ado, I'll just quickly mention some of the questions. So, first question is to both of you. Is it possible that we are seeing the planets or the received data as one of their primordial stage, and they might harbor life in their present state, which we'll never be able to see through electromagnetic waves? Sorry. Shall I repeat the question?
That might help, yes, please.
Also, there's some noise coming, actually. Yeah, okay. Is it possible that we are seeing the planets or the received data is of their primordial stage, and they might harbor life in their present state, which we'll never be able to see through electromagnetic waves?
Interesting. So I'm not sure I understood the question entirely, and Prajwal, please correct me if I'm wrong here. But I think the question is asking whether there is something we can see from planets that we cannot identify in the electromagnetic spectrum. Is that the question?
Well, pretty much, yeah.
Well, I mean, as of now, we have ways to detect several energies or frequencies in an electromagnetic spectrum. So if there's going to be a particle that is of, you know, even more lesser energy or higher energy, then I think, yeah, I mean, we will still be able to detect it, but we probably just don't have the technology to be able to detect it. But I'm still not sure I understood the question. So maybe, Prajwal, if you might.
No, actually, I didn't understand the question either. I mean, basically, we see planets, we expect to see planets by reflected light, but that's very, very feeble. So we can do that only for the planets in the solar system, not for the planets around the other stars. And so to detect those planets, we have to use other techniques, but they still rely on the electromagnetic spectrum. So, you know, typically we detect planets around other stars either by seeing the shadow of the planet eclipse the star, which will result in a little bit of dip in the amount of light that we see from the star, and just being able to detect that small little dip, we are able, and it, you know, happens at a periodic rate, so then we're able to detect the planet or the presence of the planet. And the other way is spectroscopy. So Devika just described the technique of spectroscopy, but spectroscopy is also a tool to determine the motion of an object, at least in the line of sight. And if a star has a sizable mass planet, then it will cause a wobble in the star, and therefore a periodic shift in the spectrum, and that can be detected, and so on. So there are these ways, but they all rely on data, using the electromagnetic spectrum. So I wasn't sure exactly what. I don't know if I answered the question or Devika answered the question.
I think atoms are quite quantified. So atoms have different energy levels, and we have theoretical solutions to tell us what is the different energy for the different particles. So if you find like a subatomic particle that has one energy for which we haven't theoretically solved, then yeah, we might be able to extend the electromagnetic spectrum, but in the realms of the physics of the atom and the different particles we have, we're able to solve and understand what is the energy of the subatomic particle, like a quark or even more smaller. So it really depends upon the theoretical solution of the different energy levels of the atom, I would say. It's an interesting question, if that's the question. Can you extend the electromagnetic spectrum? That's a good one. I don't know if that's the question.
If it's a long question, maybe you can, I don't know if you can copy paste, but maybe you can paste it into the chat box so we can read it. Maybe that makes it easier.
Sure, but so there's another questions as well. So okay, one of the questions is that how do we know that dark matter exists in the first place?
Yeah, by basically studying the motions and predicting the motions using the things that we think are driving gravitationally that particular system. So, for example, if you look at a particular galaxy and all the stars in it, then you measure. This was how it was first discovered. This famous experiment by Vera Rubin. So they basically measured the speeds of the stars in the galaxy and saw how the speeds changed as you moved from the center of the galaxy to its outskirts. And then they calculated the mass of the galaxy depending on the stars that they saw. So given the mass of the galaxy, that is only the sum of the masses of the stars that they saw, that predicts a certain change in the speeds at which the stars rotate. But what they found was that the stars rotated too fast in the outskirts compared to what was predicted by the mass. So at that speed, the stars shouldn't have stayed in the galaxy. They should have just shot off. So there was something holding the stars back, and we couldn't see that. So there had to be something. So that something is dark matter. So this is just one example. I mean, there's also dark matter seen in so-called clusters of galaxies and so on, but with similar techniques. So basically, dark matter can be detected through their gravitational effect, but they are not luminous, so we can't see them. So that's why we call it. It's dark,
that's
but
what
it's matter because it attracts gravitation.
That's what the follow-up question was, that how do we detect the dark matter?
Actually, can I just add to what Prajwal just said there? So when you take the mass distribution of the galaxy, ideally, because the most of the mass is concentrated in the center because of the supermassive black hole, you expect that all the mass is there, and then the stars and dust and stuff is not that much. But, at the outer parts near the halo where all the globular clusters were roaming around in a spiral galaxy, for example, the mass distribution peaked once again. So we obviously realized, and that was research from some time ago, that there must be something there that is heavy, that is contributing to the mass in the outer parts of a galaxy. And they called it dark matter because they didn't see it, but the mass distribution curve of the galaxy showed it. That's why they call it dark matter. But dark energy, again, is even more hard to predict because it doesn't even show up in a mass curve of a galaxy or whatever, right? But you need it because if you look at the model of the universe that you have and the lambda values, putting all of that into account, you need some sort of a fudge to keep the physics together that we know. And that's what they call dark energy. If you took that out, It could be anything. You can call it vanilla ice cream if you want, but it's essentially just a fudge factor to hold the equation of the universe together. So that's kind of how we really, one of the other ways, in addition to the velocity that Prajwal was talking about, that we identified or we hypothesized that dark matter should exist, and it does exist. But I think observations is, it's really hot stuff. It's really hot gas, and it shows up a lot in X-rays. There's a lot of X-ray observations and lots of studies. I think there's these surveys called DES, dark energy surveys and dark matter surveys, and they are basically looking at outer parts of the galactic halos, and also the intra cluster of, so galaxies form in clusters, and then you have intra-cluster voids, and inside there you also have X-ray emissions that have shown that, that points to the presence of dark matter. But I don't know, is there any other high energy observations, Prajwal? Do you know of any other ones that are coming from high energy studies? These are the ones I've come across, but yeah.
No, but you can do lensing studies, right? That's not really high energy, but mass causes. Sorry, is there some disturbance?
I think there's echo when you speak.
Oh, what do I do about that?
No, I think it's fine. Yeah.
Okay. This thing that we call dark matter, we don't know what it is, and it's not luminous, but it interacts gravitationally, and therefore you can see the effects on the background light. So Einstein's theory predicts that mass bends light, and the effect of dark matter in the form of bending of light can be measured. So you take images of galaxies in the sky, and you see the effects of this imprinted as distortions in the images.
Okay.
So in fact, there are certain instances where they have actually constructed images of the dark matter using the same false color technique that I mentioned. So you can represent the dark matter also.
There's one more very interesting question that has come up. How would you explain the end or death of a black hole?
Sorry, the end of a black hole?
Yeah.
Is that the question?
Okay. Yeah.
As of now, there has been no measurable evidence that black holes will have an end. So presumably they just keep accreting and growing and becoming more massive, and they might, of course, encounter other mass or regular mass, gas, stars, another black hole, whatever. Everything will sort of just go together. But there was this prediction by Stephen Hawking using sort of quantum physics and so on, that there would be something called Hawking radiation. That predicts that there will be some radiation that comes out of a black hole. And so then, if that is true, then a black hole will evaporate. But the more massive a black hole is, the slower that evaporation process is. So very, very tiny black holes, you expect them to just evaporate, just like that. Oh. But we don't know of any tiny black holes. The only black holes we have evidence for are those which we believe are the result of stellar death. And so those are at least a few solar masses. We don't know of any black holes which is smaller than those. So any black holes of that mass and higher, and definitely the ones that I talked about, which are the giant black holes with 1 million solar masses or 1 billion solar masses, they would evaporate very, 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 very slowly. So the prediction is, like slower than the life of the universe or whatever. So yeah.
Dr.
So we haven't seen evidence so far for this evaporation. So we don't know.
No, I don't. I have some science fiction to add. I think Prajwal is she's the expert, so I think what she said is perfect. But I remember
Yeah.
giving an talk to a bunch of 8-year-olds, and these are 8-year-olds, and I got asked the question, so Devika, black holes merge, and we've detected them through gravitational waves, and we've seen simulations, and I was quite impressed coming from an 8-year-old, and I thought, well, yeah, you've said it all. Can I go home? And then said to me, no, that's not my question. And I said, okay, what's coming? And he said, so if all the stars become black holes and all of them start merging, one day can we find this massive big black hole? And I said, well, I don't know. I'm not so sure. It's good science fiction, but I don't know. But I don't know.
Yeah, I mean, in principle, yes, but then you need something to bring all the black holes together.
Together,
Right?
yeah.
And the universe is expanding, so the space
That's
between things is stretching. So, the likelihood of that is going to reduce. So,
yeah. But no, I think that's perfect. Yeah.
Yeah. Actually, that was my mom's question. So
Huh?
it's no surprise that, she's, you can tell that an 8-year-old in that manner. And also, I would like to say that in Dr. Devika's slide, obviously the binary system, they danced better, I would say.
Okay. Well,
Yeah.
each one to their own. Well,
Yeah.
the funny thing about that simulation was I was trying to work on these new class of binaries, and it was quite late at night, and I was watching that, and I thought I've seen this movement somewhere. I mean, I'm quite a
Oh.
fan of dancing, so I remember this scene from Shall We Dance, and I put them together. It's just a very simple putting together.
Wow.
Worked perfectly, and I thought,
Yeah.
wow. So I actually put a grant application once called Cosmic Tango, which would actually worked. So yeah. Anyway, thanks.
That's really cool. Well, we shall be ending our session now. I want to thank Dr. Prajwal and Dr. Devika for this amazing journey you took us, and the team of SSERD as well. I would like to just invite Devinder and Namana on stage now. Thanks a lot.
Thank you, Kushi.
Yeah.
Thank you, Dr. Prajwal, for giving us the insights about Milky Way, about the vastness of cosmos, and even about the merge of galaxies, which gives us a good amount of invisible energy to learn
Namana,
about
I
space.
think okay, we can't see you.
Oh, but I'm here in the show.
Um, oh, okay, I think it's just in my screen. I'm sorry, go on.
no, I can't see anybody. It's a black screen.
Oh,
So maybe her
yeah, it is
camera's
a
off.
black screen.
Yeah,
Maybe
it
her
is.
camera's off.
No, it's actually on.
Oh, now, yeah,
There
now
it
we
is.
can see you.
Yeah,
Now we can
okay,
see you.
fine. Okay. Thank you, Dr. Prajwal, for giving us the insights about Milky Way, about the vastness of the cosmos, and even about the merge of galaxies, which gives us a good amount of invisible energy to learn about space. It was also joyful to learn about how black holes remove the undigested mass of plasma into the space. It was completely amazing to know about the connection of us humans with the cosmos. It gives me goosebumps to know that we are all a universe in ourselves. It was also interesting to know about the life cycle of stars and the birth of elements that we can see in our daily lives. Thank you, Dr. Devika, for such an insightful talk. I would like to thank both of the speakers for taking us on a virtual journey from the Big Bang to the dark matter, and especially for stopping at the black hole. Also, I would like to extend my appreciation to Kushi for wonderfully moderating this session. Thank you, Kushi. Proceeding further, let me share my screen. I would like to extend my sincere gratitude for our philanthropic sponsor, Genex Space. Genex Space is an edtech company dedicated to creating and providing high quality all around space education and services for students and institutions. Formed with the key takeaways of SSERD, a space education and outreach NGO, Genex Space is committed to igniting curiosity and preparing the young generation for this space age to solve significant challenges of our time with the help of space science and technology. We aim to educate and guide curious young minds to achieve their space dreams with space institutions, organizations, companies, startups, and professionals. We request you to go check out the courses provided by Genex Space at www.genex.space. As we like space, we also like things which depict space. When I talk about things related to space, which we can possess, I remember space merchandise. I personally prefer merchandises related to ISRO as they are a source of inspiration to me. On this note, I would like to thank our other sponsor, DSpace. DSpace is an official ISRO merchandise store. To order your set of merchandises, visit dspace.com. I would like to express my heartfelt gratitude to Nikita for giving me and Devender an opportunity to host this event. But today was just another ride in the fantasy park, and tomorrow we will be coming back with yet another ride. That is another panel of amazing speakers. Talking about the schedule for tomorrow, that is 13th of October 2021, we have talks and panel discussion by Dr. Chaitanya Giri, who is an astrobiochemist, and also Dr. Margarita Safonova, who is an astrophysicist and visiting professor at Indian Institute of Astrophysics on the topic of exoplanets and astrobiology. I have an exciting announcement. The deadlines for the competitions have been extended to 14th of October 2021. Then why wait? Just go and submit your works. And the link to submit your work is OP21comp. Please avoid plagiarism and submit before the deadline. At SSERD, we also offer internships on various topics such as propulsion system, astrobiology, astronomy, astrophysics, satellites, space settlement, and space mission design. For registrations and for more information, please visit sscrd.org. I would like to thank everyone who has joined us for this amazing session and panel discussion. I would also like to thank the audience for posting in amazing questions. Please join us tomorrow for yet an amazing session. Till then, take care.